Hello everyone, welcome to the course on digital signal processing. This is lecture number 3, and in this lecture we will see how we can design the Butterworth filter. So in our lecture first and second we have seen that the IR filters are of two types. One is called as the Butterworth filter and the other one is called as the Chebyshev filters. So we have seen various methods to map an analog frequency into a digital frequency. So we have the techniques called as approximation of derivatives. We have the impulse invariance transformation technique, and we have the bilinear transformation technique. So in this lecture, we will see that how we can design our prototype or how we can design our Butterworth low pass filter. So first of all, we'll be starting with the introduction to this type of filter, Butterworth low pass filter. So we are having the frequency response over here. So in this frequency response, we can observe that this filter is having a maximally flat in the pass band as well as in the stop band. Also, we are having the frequency response which is given by h of j omega. It is basically the magnitude response, which is a by 1 plus ohm by ohm c raised to power 2n and whole raised to power 1 by 2. So this is the magnitude response. To the right we have the magnitude response, and we can clearly see that as we are increasing the filter order, so what happened, the frequency response, the magnitude response basically approaches a response which is basically similar to that of an ideal kind of response. So the filter basically becomes the ideal. It basically approaches towards the ideal filter as we are increasing the filter order. So next, also here we have the response now. Let's say when the filter order is 1, n equals to 1, so we can see this kind of behavior we have as we are increasing the filter order, and we'll be having this type of frequency response. This is the ideal response of a low pass filter where ohm c is called as the cutoff frequency. So the cutoff frequency is the frequency at which the gain reduces to 1 by root 2 times the maximum value, or we can say when the gain reduces to 3 dB. So the particular frequency is also called as 3 dB frequency. So this we need to calculate for this low pass filter. Apart from that, there is again an important point that as we are increasing the filter order, the phase response of the Butterworth filter that will become more non-linear by increasing the value of n. So we have one advantage of increasing the value of n, and we have one disadvantage also, that the phase response become non-linear. So now we'll see that how we can design a digital Butterworth filter from the specifications, from the frequency domain specifications. So let's say we can say that since the filter the designing of the filter or the frequency response depends on the filter order n. So we'll be basically starting with the calculation of filter order from the frequencies, from the specification, from the filter specification provided. So from this particular specifications, we can see that we have A1 and A2. These are the attenuations, and we have the omega. So basically these are the specifications provided for a digital Butterworth filter. So we need to design this filter. How can we design? First of all, let us see that this omega 1 and omega 2, they are called as edge frequencies. So ohm 1 and ohm 2, they are the analog frequencies corresponding to these digital frequencies omega 1 and omega 2. So the value of these ohm 1 and ohm 2 we can calculate with the help of, since we are already aware the mapping of analog frequency to digital frequency. So we have two techniques to calculate the values of ohm 1 and ohm 2. What kind of transform we are going to use? Either it is a bilinear transformation technique or it is a impulse invariance transformation technique. So based on the both the transformation techniques, we can calculate the value of ohm1 and ohm2. Next is we need to find out the filter order. So filter order can be calculated. If we can see that, we'll put the value, the magnitude is attenuation A1 and the attenuation here A2. So we just put A1 and A2 in our last equations. So we have these two inequalities. So this can be further, if we simplify this, both the equations, both the inequalities. So we will be having, let's say, equation, this is equation number 1 and this is equation number 2, which contains the edge frequencies ohm1, ohm2, as well as the attenuations A1, A2, and also we have N. So now if we assume the equality, if we assume that these equations are equal, so we can divide equation number 2 by equation number 1, or else we can divide 1 by 2 also. So we'll be having one other equation which basically correlates the edge frequencies ohm1, ohm2 and their attenuations, respective attenuations, which is A1 and A2 respectively. So we'll further simplify this equation. We'll be having the formula to calculate the order of a Butterworth filter. So this can be given as n equals to 1 by 2 log of 1 by A2 square minus 1 and whole divided by 1 by A1 square minus 1 and divide by log of ohm2 by ohm1. Here this ohm and ohm2 by ohm1 is an analog frequency, the ratio of analog frequencies. Now, since the filter order, it's an integer quantity. So let's say if in any problem we are getting a value which is 2.36, so this can be written as 3. So n is, if n is not an integer, the value of n is chosen to be the next nearest integer. So this we need to remember. So once we just calculated with the order, the Butterworth order is calculated, then we'll be having the next important parameter which is called as a cutoff frequency. So cutoff frequency means it will decide where the gain reduces to 3 dB. So in our last equation, if we can solve this equation number 1 by assuming this as equality, so we can have a equation is ohmc equals to ohm1 divided by 1 by A1 square minus 1 whole raised to power 1 by 2n. So these two equations are quite important. Let's say we'll mark this as equation number 3, this is equation number 4. So both the equation number 3 and 4 will give us the parameters which are important, which are very, very crucial for designing of a Butterworth low pass filter, let's say, where n is called as the order of the filter and ohmc is called as the cutoff frequency of the low pass filter. So now we'll be seeing some important result over here. So these are called as a filter specifications. So filter specifications generally are given in the digital form. These are in a digital form. So we'll be seeing some steps, that what are the steps behind to the designing of a Butterworth filter. So these are the frequency specifications provided, where A1 and A2 are the attenuation in the pass band and stop band respectively, and these frequencies ohm1 and ohm2 are the frequencies for the cutoff, means the edge frequency for a pass band and for a stop band. So we have seen both the results. First is to calculate the order and the second is to calculate the cutoff frequency of the filter. So we'll be utilizing both equations to design a Butterworth low pass filter. So we'll see next what is the transfer function for a what is the generalized transfer function for a Butterworth low pass filter. So we have basically, I'll tell you two type of transfer functions. One is a unnormalized transfer function and another one is called as a normalized transfer function. So what we can see here is that if the filter order is even or if the filter order is odd. So we have two approaches. First is when n is even. Let's say we have 2, 4, 6 and so on. So what is a transfer function for an analog, this we called as analog prototype filter. prototype filter. So this HAS is the transfer function of an analog prototype filter, which is pi k equals to 1 to n by 2 ohm c square divided by s square plus bk ohm cs plus ohm c square. Similarly, if n is odd, let's say if n is 1, 3, 5, 7 and so on, so there is bit change. There is one factor which is ohm c divided by s plus ohm c outside, where bk can be calculated as 2 sine 2k minus 1 pi divided by 2n. So we can calculate the value of bk if we'll put the values of k from we can see from this summation also. For this pi k equals to 1 to n minus 1 by 2, means we have these terms available in a product form, product of sum, we can say. So if we want to calculate, if we want to see the normalized transfer function, so what we need to do is we need to just divide the numerator and denominator by a factor of ohm c. So in our last equations, when n is even or n is odd, so both the transfer functions will give you Sn. Sn is nothing but the normalized value, Sn square plus bk Sn plus 1. And similarly, we have the transfer function, the analog prototype transfer function, when the filter order is odd. So this again we need to remember that whether we have to design a unnormalized filter or we need to design a normalized filter. Accordingly, we can use the transfer functions. Now we'll see, this is a very, very important part, that what is the design procedure for a low pass digital Butterworth IR filter. So first we'll start with the specifications, frequency specification of a low pass digital Butterworth filter. So first we have A1 and A2. So A1 and A2, they are the gains at the passband frequency, which is omega 1, and similarly A2 is the gain at stop band frequency, which is called as omega 2. Similarly, as we have already seen that ohm 1 and ohm 2, these are the corresponding analog frequencies corresponding to omega 1 and omega 2 respectively. So we can calculate ohm 1 and ohm 2 depending upon what mapping method we are going to use. Either it is a BLT, bilinear transformation, or it is a IIT. So first step, we need to choose a transform. So in the beginning itself, it may be mentioned, or it must be mentioned definitely, that which method you have to use. So choosing the type of transformation technique, either we are using BLT or IIT. This is the first step. Now we'll calculate the ratio of the analog edge frequency, which is ohm 2 by ohm 1. So for bilinear transformation, we have the formula ohm 1 equals to 2 by t tan of omega 1 by 2. Similarly, ohm 2 also can be calculated for the bilinear transformation. So the ratio, which is ohm 2 by ohm 1 equals to tan of omega 2 by 2 and tan of omega 1 by 2. So this is for BLT. But let's say if the frequency transformation technique which we need to use is IIT, impulse invariance transformation. So accordingly, we are also aware that ohm 1 equals to omega 1 by t. So again, we can calculate the ratio. It is nothing but the ratio of the digital frequencies. Means separately, we don't need to calculate what is ohm 2 and ohm 1, because the ratio will be, it is nothing but the ratio of the digital frequency only. So this is the second step. Next, so once we have decided that which method we are going to use, so we have a generalized formula to calculate the order corresponding to the Butterworth filter. So if we have the ratio ohm 2 by ohm 1, also we are having these attenuations A1 and A2. So with the help of this formula, we can calculate the filter order. So let's say if the filter order is in the form of decimal form, let's say if it is 2.5 or let's say it is 3.2. So we can choose the next. Now, after the filter order, we need to calculate that what is the cutoff frequency of the low pass filter. So cutoff frequency can be calculated if we have this entire relationship, which is ohm1 divided by 1 by a1 square minus 1 whole raised to power 1 by 2n. So again, the cutoff frequency will depend which type of method we are going to use. Either we are using BLT or we are using IIT. So the cutoff frequency, the relationships for both the means bilinear or impulse invariant transformation method will be varied accordingly. So this is step number 4. Now once the filter order is calculated, now we will be able to decide that what kind of transfer function we have, right? Means if the filter order is even or the filter order is odd. Accordingly, we can write down that what is the transfer function, of an analog prototype filter, or we can say analog prototype low pass filter. It is the correct word. So we'll be able to calculate the value of BK also once we are having the value of n. And for normalized case, we can see that ohm C equals to 1 also, 1 radian per second. Accordingly, we can write down the transfer function for the normalized Butterworth filter. Now next is, since we have designed up analog low pass filter, but we are interested in designing a digital filter. So accordingly, at this particular stage, we need to further choose that how we can transform this analog low pass filter into a digital transfer function. So we will be having the method. Accordingly, we can use any of the method, and we are already aware that how these two methods can be applied to any analog transfer function, so that it will become a digital transfer function, or it will become a system function. So once this HZ is known, the system function of a low pass filter is known. Now we can use the realization. What type of realization we are having? Either we want to design this direct form structure, we want to design this cascade structure, parallel structure, any kind of ladder structure will be able to realize. So these are certain steps. So here we have seen that how we can design, how we can use this design steps to transform a low pass filter to a low pass filter. Later on, we'll see that how we can use the frequency transformation technique either in a digital or in analog form to transform a low pass filter into some high pass, band pass or band reject filter. So on this particular topic, we'll be having one numerical that we need to design a Butterworth digital filter with the help of BLT, bilinear transformation, and this frequency specification for the desired digital low pass filter are known with t equals to 1 second. So as from this frequency specification, it is clear that we have the attenuation in pass band and the attenuation in stop band. Also, we'll be able to calculate, we'll be able to see what is omega 1 and what is omega 2. So this we'll be able to basically directly check that what type of frequency response is given. Now based on these specifications A1, A2 and omega 1 and omega 2, we can see that we have the bilinear transformation. As per the requirement, we have to use the BLT. So for BLT, we'll be using the method, we'll be using the frequency transformation. How we can transform this digital frequency into corresponding analog domain. So we use this particular formula to calculate, and we are getting a value which is 4.82. Similarly, ohm1 can also be calculated, and the value is 2. So now the second step was to calculate. We are interested in finding the ratio, which is ohm2 by ohm1, which is nearly around 2.414. Now we'll be using these ratios, ohm2 by ohm1, and also along with the values of attenuations A1 and A2 to calculate the filter order. Now we'll put this, and by solving this, we'll be getting that n must be greater than equal to 2.626. So as we are already aware that filter order can't be a decimal value, it will be a value which is which is next nearest integer value. So 2.62, it will be treated as n equals to 3. So once it is decided that the filter order is odd, so we'll be able to choose the proper transfer function. Before that, we are interested in finding the cutoff frequency also with the help of BLT technique. So the cutoff frequency, which is also called as minus 3 dB frequency, because at this particular frequency gain reduces to 3 dB. So we can see that we are getting a value which is 2.546. So once now the cutoff frequency is calculated, the filter order is calculated, we'll be able to write down the transfer function of an analog prototype low pass filter. So which is given by HAS, and the filter order was odd. So if the filter order was odd, we have already seen that what kind of transfer function is there. Now n equals to 3, so 3 minus 1 is 2, 2 by 2 is 1, so k equal to 1. So if k equals to 1, we have only b1. So if k equals to 1, we can easily calculate what is the value of b1 and we can put in our transfer function. So yeah, if n equals to 3, we'll be having b1, the value is 1, and finally it will put those values of ohm C and this b1. So we're getting a transfer function which is HAS. Now this HAS can be further converted to HZ because we are interested in designing a digital Butterworth low pass filter. So we are having certain steps that how we can convert this HAS into HZ by using BLT. So in BLT it is quite easy that if we'll use the mapping factor S equals to 2 by T, 1 minus Z inverse divided by 1 plus Z inverse. If we can substitute the value of S in our last equation, so I'll be getting a transfer function which is called as a digital filter transfer function HZ. So just further after simplifying this, we are getting the value of HZ like this. Now this HZ can be further realizable also. We can realize this with the help of direct form 1, direct form 2. Also we can realize this with the help of cascade. So these are the steps. Now we have a similar kind of example over here where we have different attenuations, which is under root of 0.5 and 0.2. But here we have to use the impulse invariance transformation technique. So before starting with this, we must pen down that what are the steps behind the designing of a Butterworth filter. So first is the method we need to mention. So method is IIT we need to choose. Second step is from these specifications we need to write down what is A1, what is A2, what is omega 1, what is omega 2. Once these frequencies are known, the third step is with the help of impulse invariance transformation, we need to calculate what is ohm 1, what is ohm 2 corresponding to omega 1 and omega 2. Also we at this particular stage, we are interested in finding the ratio which is ohm 2 by ohm 1. Next is, once this ratio is calculated, we are interested in calculating the filter order N. Next, fifth step, we are interested in finding the cutoff frequency, which is nothing but ohm C. With the help of the method we need to use is IIT. Right, once the cutoff frequency is calculated, the sixth step is to find out the transfer function, analog transfer function, analog filter transfer function. So we can choose the corresponding analog filter transfer function based on if the filter order is even or the filter order is odd. So once the transformation is written, so we'll be able to basically calculate what is the value of HAS. Now in the next step, eighth step, we'll be able to transform that how this analog low pass filter is transformed into the corresponding Dushyant filter by the help of mapping technique. Here the mapping technique was IIT, impulse invariance transformation technique. So these are certain 8 steps to design a Butterworth, digital Butterworth low pass filter. So clearly we can see here, these are the steps. We have calculated the filter order. So the filter order was E1. We have calculated the value of B1, B2. We have the coefficients, filter coefficients, and we have the HS, the analog, the transfer function of an analog prototype low pass filter. Afterwards, we are following certain process to calculate the value of HZ. We are already aware that how we can calculate HZ from HS. We just want to make this HS in a standard form so that we can directly write down its corresponding HZ. So this is nothing but HZ, which is in terms of H1 plus H2. So this is our final result over here. Now, some properties of Butterworth filter. So Butterworth filters are all pole design. That is, the zero of the filter exists at some z equals to infinite. The filter order n completely specify the filter. The magnitude response approaches the ideal response as we are increasing the filter order. The magnitude response is maximally flat type in the pass band as well as in the stop band. The magnitude is monotonically decreasing function of ohm, which is the frequency. The cutoff frequency ohm C, the magnitude of the normalized Butterworth filter is 1 by root 2 times the maximum value. Hence, the dB magnitude at the cutoff frequency will be 3 dB less than the maximum value. So these are certain properties of the Butterworth filter. These are the references. Thank you.